Let's have a look at areas in a bit more detail. So here's some random function. If we wanted to find the area, well, we've normally just been saying, oh, the area between the curve and the axis, but in this case, what area am I talking about? Because am I talking about the bit underneath? Am I talking about the bit above the axis? Or am I talking about both? I mean, what area are we talking about? So say I wanted to find from A to B. Well, that's no drama. That's all completely above the axis, so I know I'd integrate from A to B. And if I wanted to do B to C, that's all below, so it would be the negative of the integral, because the integral would give me a negative answer, so if I want to find the area, it would be the negative of that. If I went from A to C, I can't just integrate from A to C, because some is above, some is below. So we do have to separate it into its two different areas and add them together. So area below the axis, as I just said, we could find the negative of the integral. You could find the absolute value. Some people do that when they're too lazy to draw a diagram, and so they just do their integral. They come up with a negative answer and so go, oh damn, must have been below. Not a problem. Absolute value, absolute value, absolute value, absolute value. Oh, equals, there you go, I've got the answer. Some people do that. Of course, the other way, if you do know what it looks like, you could just swap the limits around. And that would turn that negative area into a positive area. Now, y equals x cubed, if I wanted to find from -1 to 1. Okay, well, some of it's below, some of it's above. So it would be negative the area below, -1 to 0, positive the area above, 0 to 1, and add 1 to the power over the power. Amazingly, they turn out to be the same when we integrate, and we end up with a half unit squared. And that's probably how Girish would do it. Unless, of course, we notice symmetry. So in this case, we'd do it like an even function. You could do it twice from twice to 0 to 1, just like, as I say, an even function. Add 1 to the power over the power, and of course we get a half. Okay. Well, it looks symmetric, but I don't know for sure. So this time I am going to have to split it up. So I'm going to integrate from -2 to 1, and that'll be above, and then it'll be the negative from -1 to 0. But again, when we integrate these things, we will get the same answer because it's the same function. Notice what I've done though. I've turned it into a positive rather than a negative. Now the reason I've done that is because have a look at the position of the limits. On both of those, -1's on the top. Okay, it's going to save me a little bit of time. Because instead of substituting the first one and going, oh, I'll sub in -1 minus sub in -2, and then in the second one, oh, I'll sub in 0, sub in -1, I know, well, hang on, no, I'll just work out twice when I sub in -1 and then subtract -2 and subtract 0. So I've swapped them round so the limits are the same, and that, well, saves me a little bit of time, I suppose. Not a huge amount, but it does save me some time. All right, what happens if the area, instead of going to the x-axis, we're going to the y-axis? Well, this time, because we're going to the y-axis, I need to make x the subject. So x will end up being some function of y. Now, I've called it gy instead of fy because, well, there's no guarantee it would be the same function, of course. And we'd have to substitute in the y coordinates rather than the x coordinates. But then we can do it pretty much the same, but now we're integrating with respect to y. Now, if you're ever unsure which one, it's very easy to tell. We're going to the y-axis, so it must be the y. So let's do an example of that. Here we have a parabola. Don't make the mistake of thinking it's twice that. It's still the same idea, just because it's on its side. We're just going to the axis. It's not like, oh, because all of a sudden, because it's vertical, now we must look at both sides of the axis. The question we're interested in is just that area there. But I've been given the x values, so let's work out the y values. Rearranging x would be y to the power of a quarter. Now let's work out the y values. 1 to the power of 4 is 1. 2 to the power of 4 is 16. So I'm integrating from 1 to 16 here. Add 1 to the power over the power. Sub in. In this case, I don't need to put it back into surd form because I know the 4 through to 16. Well, clearly it must be 2. That's where we just came from. So I know it's 2 to the power of 5 minus 1 to the power of 5. Times that by 4/5 and we get 124 and 5. Well, what happens if I'm trapping an area between two random curves? So here's y equals function x, there's y equals g of x, and I want to find the area trapped between the two curves. Okay. Well, the point of intersection would be handy. Probably more interested in the x value. For this one, I don't really need to know the y value. So let's call them A and B. And I suppose if we were to do each question separately, if I was to find the area under the red curve, then find the area under the blue curve, clearly the area between must be the difference between the two. So I'm just subtracting it. So I get this, integral from a to b of function x minus a to b of g of x. But of course our rules of integration, we can write that all as one integral. So it's just the difference between the two functions is what we'll integrate. So let's do this. We're going to find the area enclosed between x to the power of 5 and y equals x. Now, it's going to make a difference. We need to know which one's on top. Because if I get the wrong one, I'll end up with a negative answer because I'll be subtracting in the reverse order. And so don't be lazy. It doesn't take that long to draw a quick sketch. Y equals x is, of course, the straight line. X to the 5 is a cubic, but it's flatter at the base, steeper at the sides. I might have exaggerated that just a little bit there. Make sure you read the question carefully. They just want the area in the positive quadrant. So there's actually two sections there trapped between the two, but they're only interested in that bit there. So the line is clearly on top. We're going to have to find the point of intersection. Now, just in case you can't quite look at that and go, I wonder where they meet, you could, of course, solve them simultaneously. So x to the power of 5 equals x. Oh, well, that factorised. Oh, look, naught plus or minus 1. So, in fact, we found all three. Clearly, the ones we're interested in are naught, and that one up there would be x equals 1. So we're going from naught to 5, top boundary minus the bottom boundary, add 1 to the power over the power, and we get a third. We don't have to worry, when it's an area between two curves, we don't have to worry about above the axis and below the axis. Right? Because it doesn't make a scrap of difference when you're going between the two. So between two curves, you don't have to worry about below and above. All right, 2002. Oh, quite an old question now. So they want us to find, well, they've told us that the two graphs intersect at the point 4, 0 and A. I think the word and's missing there. So, and the point A. Question 1 for 2 marks. Find A. Solve them simultaneously. So x minus 4 equals x squared minus 4x. So we end up with two possibilities. One of those we already knew. That's the point 4, 0. So therefore A must be the point 1. And okay, a little bit of work to be done. We have to work out the y value. Negative 3. Find the area of the shaded region. Well, top one minus the bottom one. Top one was the line. Bottom one's x squared minus 4x. So that's what we're integrating. Minus x squared plus 5x minus 4. Add 1 to the power over the power. Substitute in 9 on 2 units squared for 3 marks. Also from a tutor paper, but a little bit more interesting. So you can see it's question 8, a bit later in the paper, so a bit of thought needed here. So they've told us what we've got. We've got a circle of radius 2 and our parabola with the equation x squared minus 3x plus 2. They've given us a hint. By considering the difference of two areas, find the area of the shaded region. Now, of course, it's up to us which two areas we choose to use. Now, the problem is with this one, if I was just to go top one minus the bottom one, I have a problem because it's not consistent. Because here we're going to the axis, once we go past x equals 1, the bottom boundary is now the x-axis, not the parabola. So is that what they meant by considering two areas? So if we break it up into those two areas, I'm going to go from 0 to 1 of the circle minus the parabola, and then from 1 to 2, simply just the circle. Perhaps that's what they meant. Okay. No, that's not what they were talking about. Because remember, that would be adding. Their hint was by considering the difference. So if you read their hint carefully, it's giving you a huge clue. Don't do it that way. Because the other way we could do it is go, oh, let's find the area under the parabola from 0 to 1 and just subtract it from a quarter of the circle. See, that would give you the same area. And that's going to be easier. So a quarter pi r squared minus the integral from 0 to 1 of the parabola. Add 1 to the power over the power. And eventually there is pi minus 5/6. So read them very carefully because sometimes they're giving you clues. Okay.